For most of human history, the greatest threats to Earth came from within our own solar system. Asteroids, comets, objects we could track, objects we could predict. But in the last decade, astronomers discovered something unsettling. Not everything near Earth comes from here. In 2017, an object called Oumuamua passed through our solar system. It came from interstellar space. In 2019, 2I Borisov followed, a comet from another star. In 2025, 3I ATLS confirmed that these visitors are real, natural, and more common than we once believed. These objects are not bound to the sun. They don't follow predictable orbits. They arrive fast and they leave forever. Now imagine this. What if one of them didn't miss? What if an object from another star system was headed directly toward Earth? Unlike typical asteroids, interstellar objects travel much faster. They carry more energy, they give less warning, and they don't care about the rules we're used to. This is not science fiction. This is physics. And today, scientists are asking a serious question. If an interstellar object hit Earth, would we even see it coming? That's the question this documentary explores. Not to create fear, but to understand a new kind of cosmic risk that humanity has only just discovered. Because Earth has survived many impacts before, but never one from another star. What are interstellar objects, and why they matter? For centuries, astronomers believed that every object moving near Earth belonged to our solar system. Asteroids came from the asteroid belt. Comets came from the Kuiper belt or the Oort cloud. Everything had an origin tied to the sun. That belief shaped how we measured risk. It shaped how we tracked threats. And it shaped how safe we believed Earth was. Then, in 2017, that assumption quietly collapsed. The first crack in the old model. In October of that year, astronomers detected a faint object moving unusually fast through the inner solar system. At first, it looked like a normal asteroid, but when scientists calculated its orbit, something didn't make sense. It wasn't slowing down. It wasn't curving back toward the sun. Its path was hyperbolic, meaning it was not gravitationally bound to our star. The object was named Oumuamua, a Hawaiian word meaning a messenger from afar arriving first, and that name turned out to be accurate. Oumuamua was the first confirmed interstellar object ever observed passing through our solar system. It had not formed here. It did not belong here. It was only visiting. Why that discovery changed everything. Before Oumuamua, interstellar objects were theoretical. Astronomers believed they must exist because planet formation is chaotic and many objects get ejected into space. But belief is not evidence. Oumuamua provided evidence, and with that evidence came a realization. Interstellar objects are real, and they move through our region of space. Just 2 years later, in 2019, a second visitor appeared. This one was different, clearly comet-like, actively releasing gas and dust. It was named 2I Borisov. Unlike Oumuamua, which behaved strangely and sparked debate, Borisov behaved exactly like a comet. Just one problem. It was moving too fast, and its orbit confirmed it also came from outside the solar system. 2 discoveries, 2 interstellar visitors, in just 2 years. Then came the third. In 2025, astronomers detected 3I ATLS. This time, there was no debate. Its interstellar origin was clear, its cometary behavior was clear, and its chemistry could be studied in detail. 3 confirmed interstellar objects in less than a decade. That number forced scientists to ask a serious question. How common are these things?
If we've detected 3 already, how many have we missed? Astronomers now believe that interstellar objects may be incredibly common. The Milky Way is violent. Stars form with massive disks of material. Planets migrate. Gravity throws debris outward. Every planetary system likely ejects billions of objects. Most drift forever. Some pass near other stars. A small fraction pass through solar systems like ours. Earth has likely been crossed by countless interstellar objects over its 4.5 billion year history. We just didn't know how to see them. Why we're only finding them now? The reason is simple: technology. Modern sky surveys scan the entire night sky repeatedly. They look for motion. They don't care where an object comes from, only that it moves. Before these surveys existed, interstellar objects passed unseen, invisible against the background of stars, gone before anyone noticed. Now we're finally opening our eyes, and what we're seeing is unsettling. Interstellar objects are not like asteroids. Here's the key difference. Asteroids orbit the sun. Their paths are predictable. We can calculate where they'll be decades in advance. Interstellar objects do not orbit the sun. They enter the solar system once and leave forever. They move faster, often 2 to 3 times faster than typical near-Earth asteroids. That extra speed means more kinetic energy. More energy means more damage if an impact occurs. A small interstellar object can hit with the force of a much larger asteroid. Energy is the real danger. Impact damage isn't just about size, it's about velocity. An interstellar object traveling at 60 to 70 kilometers per second carries enormous energy, much more than an asteroid moving at 20 kilometers per second. That means a smaller object, same destruction, less warning time. This combination makes interstellar objects a uniquely dangerous category. Why detection is so difficult? Here's the uncomfortable truth. We are not good at spotting them early. Interstellar objects arrive from any direction, including from above or below the plane of the solar system. Many come from the direction of the sun, where telescopes can't look. By the time they emerge from the glare, they're already close, and because they're moving fast, they don't stay visible long. Days, sometimes weeks. That's not much time to detect, analyze, and respond. Earth's new risk category. This is why scientists now consider interstellar objects a new class of threat, not because they are common impacts, but because they are unpredictable. They don't follow the rules our planetary defense systems were designed for. Asteroids are like scheduled visitors. Interstellar objects are strangers who don't knock. And that leads to the next question. If an interstellar object was actually headed toward Earth, would we even see it coming? That question is no longer theoretical, and in the next part, we'll explore exactly how fast these objects move and why speed changes everything.
Why interstellar objects are so fast and why speed changes everything. When it comes to cosmic impacts, size is not the most dangerous factor. Speed is. Most people imagine asteroid impacts as slow, inevitable collisions. A rock drifting through space, eventually falling toward Earth. That image is wrong. The difference between orbiting and invading. Asteroids and comets from our solar system are gravitationally bound to the sun. They orbit. That means they follow predictable paths and move at relatively moderate speeds. Typically, asteroids 15 to 25 kilometers per second, comets 20 to 30 kilometers per second. These speeds are already catastrophic, but interstellar objects are playing a different game. Interstellar objects are not orbiting the sun, they are passing through. They arrive with speed already built in, speed gained from their original star system
and from galactic motion itself. By the time they reach Earth's neighborhood, interstellar objects can be moving at 50 to 90 kilometers per second, sometimes even faster. That's up to 3 times faster than typical asteroids. Why speed multiplies destruction? In physics, impact damage depends on kinetic energy, and kinetic energy increases with the square of velocity. That means if speed doubles, energy doesn't double, it quadruples. So an interstellar object, half the size of an asteroid, moving 3 times faster, can deliver many times more energy. This changes everything. A city-killer asteroid becomes a regional catastrophe. A regional impact becomes a global climate event. Speed turns small objects into massive threats. Why interstellar objects move so fast? Interstellar objects are not just fast, they are fast for a reason. They were born in violence. In young star systems, giant planets migrate. Gravitational interactions are chaotic. Objects get slingshotted outward at enormous speeds. When an object escapes its star completely, it doesn't slow down. There's nothing to stop it. For millions or billions of years, it drifts through the galaxy, carrying that original velocity. Then it enters another star system, like ours. The sun's gravity accelerates it further. By the time it crosses Earth's orbit, it is moving faster than anything our planet defense systems were designed to handle. No second chances. Asteroids orbit the sun. If we detect one early, we can track it. We can calculate future encounters. We can plan deflection missions years in advance. Interstellar objects don't give us that luxury. They don't come back. They don't repeat. They appear once, and they leave. If one is on a collision course with Earth, there is no rehearsal, no second opportunity. The warning time problem. Speed also destroys our most important advantage, time. A typical near-Earth asteroid can be detected years or decades in advance. An interstellar object might be detected weeks before impact, days before impact, or in the worst case, after impact. Many interstellar objects approach from the direction of the sun. That means telescopes can't see them until they're already close. By the time they emerge from solar glare, they may be moving too fast for any meaningful response. Atmospheric entry at extreme speed. If an interstellar object hits Earth, its speed changes how it interacts with the atmosphere. At extreme velocities, air compresses violently, temperatures skyrocket instantly, shock waves form ahead of the object. Instead of slowing gradually, the object may explode in mid-air with massive energy release, or it may strike the surface before the atmosphere can break it apart. Either way, the results are devastating. A realistic impact scenario. Imagine an interstellar object only 100 meters wide. That sounds small, but at 70 kilometers per second, it carries energy comparable to tens of thousands of nuclear weapons. The impact would produce a blinding flash, a shockwave flattening everything nearby, fires ignited across hundreds of kilometers, a towering plume of debris. If the impact occurs on land, entire regions are destroyed. If it occurs in the ocean, massive tsunamis follow. Speed ensures there is no gentle outcome. Why Chicxulub still matters. The asteroid that ended the dinosaurs was not interstellar. It came from our solar system, and it still caused a global mass extinction. An interstellar object with similar energy could be smaller and still produce similar consequences. This forces scientists to rethink impact risk entirely. It's not just about size anymore, it's about velocity. A threat we're not ready for. Planetary defense systems today are designed around known objects, objects with orbits, objects with predictable motion. Interstellar objects don't follow those rules. They don't give long warnings, they don't arrive slowly, they arrive fast, and they leave no margin for error. This doesn't mean Earth is doomed. Interstellar impacts are still rare, but they are no longer impossible. And now that we know these objects exist, ignoring them is no longer an option. Which brings us to the next problem. Even if an interstellar object is coming, how would we even detect it in time? That question leads directly to the most uncomfortable truth of all.
Why we might not see it coming. The detection blind spots. If an interstellar object were on a direct path toward Earth, the greatest danger wouldn't be its size. It wouldn't even be its speed. The greatest danger would be something far more unsettling. We might not see it in time. The illusion of safety. From the outside, it appears that humanity is constantly watching the sky. Powerful telescopes, global monitoring networks, planetary defense programs. It feels reassuring, but that confidence hides a critical weakness. Our detection systems were built for objects that belong to the solar system, asteroids that orbit the sun, comets that return on long schedules. They follow predictable paths. Interstellar objects do not. The solar blind spot. The most dangerous detection gap lies in the direction we can't observe well, the sun. Ground-based telescopes cannot look close to the sun without being blinded. Space telescopes have similar limitations. That creates a permanent blind spot. If an interstellar object approaches Earth from the direction of the sun, it can remain invisible until it is dangerously close. By the time it emerges from solar glare, it may already be moving faster than we can react to. Days, sometimes hours. Why this is especially dangerous for interstellar objects. Asteroids usually approach from within the plane of the solar system. Interstellar objects can arrive from any direction, above the solar plane, below it, or straight toward the sun. That means our detection systems are facing a three-dimensional problem with two-dimensional coverage. Many interstellar objects are only discovered after they pass Earth. Some are detected while leaving, some are missed entirely. Speed reduces visibility time. Speed doesn't just increase damage, it reduces detection time. An asteroid moving at 20 kilometers per second can remain visible for months. An interstellar object moving at 70 kilometers per second can cross the inner solar system in weeks. That dramatically shortens the observation window. Every day lost matters. Every delay compounds the risk. Size makes it worse. Interstellar objects don't need to be large. A 50-meter object can still cause regional devastation, but smaller objects are harder to see. They reflect less sunlight. They remain faint until close. A small, fast interstellar object approaching from the sun's direction is the worst-case scenario. The Oumuamua lesson. When Oumuamua was discovered in 2017, it had already passed its closest point to the sun. By the time scientists realized what it was already leaving. There was no chance to study it up close, no chance to intercept, no chance to test defensive strategies. That discovery taught astronomers an uncomfortable lesson. We didn't detect the first interstellar object until it was already gone. How many have we missed? Based on current models, astronomers now believe that interstellar objects may pass through the inner solar system every year, possibly more. Most are small, most go unnoticed, but statistically, some will be large enough to matter. Earth has existed for billions of years. The odds say interstellar objects have crossed its orbit many times. We just weren't looking. The limits of current planetary defense. Planetary defense programs today are excellent at tracking known threats. Given enough time, we can redirect an asteroid, we can change its orbit, we can prevent an impact. But all of those strategies depend on one thing: early detection. An interstellar object detected weeks before impact offers almost no options. Deflection missions take years to plan. Emergency response only helps after impact. There is no technology today that can stop a fast, incoming interstellar object on short notice. Hope on the horizon, but not yet. The future does offer hope. Next-generation observatories are designed to watch the sky continuously.
The Vera C. Rubin Observatory, for example, will scan the entire visible sky every few nights. This dramatically increases our chances of detecting fast-moving objects, including interstellar ones. But even Rubin has limits. It cannot see through the sun. It cannot detect everything. No system can guarantee early warning for every possible trajectory. A new category of risk. This is why scientists now classify interstellar objects as a low-probability, high-impact risk. The chance of an impact is small, but the consequences are enormous, and the warning time may be minimal. This doesn't mean panic is justified. It means preparation matters. Understanding the risk matters, because the universe does not schedule events around our readiness. The hard truth. Earth has been hit before. It will be hit again. That is not speculation. It is history. The only question is, will the next impact come from our own solar system or from another star entirely? And if it does come from another star, will we see it in time? In the next part, we'll explore what actually happens if an interstellar object hits Earth. Not speculation, not exaggeration, just physics.
If an interstellar object hit Earth, realistic impact scenarios. When people imagine an impact, they usually picture one extreme: dinosaurs, global firestorms, the end of everything. But the reality is more complex. Not every impact ends the world. Some end cities, some reshape regions, and some quietly change the planet for generations. With interstellar objects, the danger is not just what hits, it's how fast it hits. Scenario 1. A small interstellar object, 20 to 50 meters. At first glance, a 30-meter object doesn't sound dangerous. That's smaller than many asteroids we already track, but speed changes the outcome. An interstellar object of this size could enter Earth's atmosphere at 60 to 80 kilometers per second. At that velocity, the atmosphere doesn't slow it gently, it compresses violently. What happens next? The object superheats instantly. Air in front of it turns into plasma. Within seconds, the object either explodes in the air or strikes the surface before fully breaking apart. The result would be similar to, but far more energetic than, the Chelyabinsk event in 2013. Windows shattered across cities, shockwaves injured thousands, but scaled up. A 30-meter interstellar object could release energy equivalent to multiple nuclear weapons. Damage outcome. Entire city districts flattened, fires ignited across tens of kilometers, infrastructure collapse, thousands to hundreds of thousands of casualties. This would not end civilization, but it would be one of the worst disasters in human history, and it could happen with almost no warning. Scenario 2. Medium interstellar object, 100 to 300 meters. This is where things escalate dramatically. A 150-meter interstellar object traveling at extreme speed would carry global-scale energy. Not extinction level, but world-changing. Atmospheric entry or impact. At this size and speed, two outcomes are possible. Airburst scenario. The object detonates in the atmosphere. The explosion releases energy greater than the largest nuclear weapon ever tested. Surface impact scenario. The object survives atmospheric entry and strikes land or ocean. Either way, the effects are catastrophic. Land impact effects. Craters several kilometers wide, shock waves flattening regions, earthquakes triggered nearby, massive firestorms, debris launched into the upper atmosphere. Ocean impact effects. Mega tsunamis hundreds of meters high near impact, coastal cities destroyed, global shipping crippled, long-term ocean ecosystem damage. Climate consequences. Even without a dinosaur-level impact, the amount of dust and soot thrown into the atmosphere could cool the planet temporarily. Crop failures, food shortages, global economic collapse. Not extinction, but a civilization-level crisis. Scenario 3.
Large interstellar object, 500 meters to 1 kilometer. This is the nightmare scenario. Rare, but not impossible. A kilometer-scale interstellar object would not need to be as large as the Chicxulub asteroid. Its speed would compensate. Energy release. At interstellar velocities, the impact energy would rival or even exceed the event that ended the age of dinosaurs. Immediate effects. Global firestorms, mega earthquakes, worldwide tsunamis, atmospheric shock waves circling the planet. Long-term effects. Sunlight blocked by dust, rapid global cooling, collapse of food chains, mass extinction event. Human civilization would not survive intact. Modern society would collapse. Whether humanity itself survives would depend on location, preparation, and sheer luck. Why interstellar impacts are different. The danger of interstellar objects is not that they are bigger, it's that they are faster and unpredictable. They don't give years of warning. They don't follow known paths. They don't allow gradual response. Even a relatively small object can cause outsized damage. No time for evacuation. For asteroid threats, early detection allows options: evacuation, deflection, preparation. For an interstellar object detected days before impact, there is no evacuation, no deflection, only aftermath response. The probability question. At this point, a critical question arises. How likely is this? The answer is uncomfortable. Large interstellar impacts are extremely rare. They may occur once in tens or hundreds of millions of years. But small and medium interstellar impacts are likely far more common. They just haven't been recognized yet. Earth's geological record may already contain such impacts. We simply haven't learned how to identify them. Why scientists take this seriously? This isn't about fear, it's about awareness. As detection improves, interstellar objects will stop being surprises. They will become statistics. And when you understand the physics, you realize something important. Earth is resilient. Civilization is fragile. Which brings us to the final question. If an interstellar object were coming, could we stop it? Or would we simply have to endure the impact? That question leads directly to the final part of this documentary.
Can we stop an interstellar object? The limits of planetary defense. When the idea of stopping an asteroid comes up, most people imagine something familiar: a spacecraft, a controlled mission, a calculated push. Humanity changing the course of a cosmic threat. And for solar system asteroids, that idea is no longer science fiction. But interstellar objects are different, and that difference matters more than most people realize. The one thing all deflection plans depend on. Every planetary defense strategy, every mission concept depends on a single factor: time. Asteroid deflection works because asteroids orbit the sun. They come back. They can be tracked years in advance. NASA's DART mission proved this. By impacting a small asteroid moon years before any danger, scientists successfully changed its orbit. Small push, big result. But that success hides a critical truth. It only worked because we had years of warning. Interstellar objects break the timeline. Interstellar objects don't orbit. They don't return. They appear once, and they move fast. In the worst-case scenario, an interstellar object could be detected weeks before impact, days before impact, or not at all. There is no realistic way to launch a deflection mission in that time frame. Rockets take months to prepare. Spacecraft take years to design. Missions require planning, testing, and coordination. Interstellar objects don't wait. Could we use nuclear weapons? This question always comes up. Could we destroy an interstellar object with nuclear weapons? The honest answer is, not reliably.
Nuclear deflection concepts depend on precise targeting, long preparation time, and known structure. With an interstellar object, structure is unknown, composition is unknown, warning time is minimal. At extreme speeds, even fragments become deadly. Breaking an interstellar object apart might make the situation worse. Instead of one impact, Earth could face a shotgun blast of high-velocity debris. What about lasers or exotic technology? You may hear about space-based lasers, gravity tractors, advanced propulsion. These ideas are promising for the distant future, but today they exist mostly on paper. None are operational. None can respond in days. None can handle an object arriving unexpectedly at interstellar speed. The hard reality? With current technology, a fast interstellar object detected late cannot be stopped. The only realistic responses would be emergency warnings, civil defense measures, and impact mitigation after the fact. That's not defeatism, it's physics. Why this doesn't mean Earth is doomed. Here's the part that matters most. Interstellar impacts are rare, extremely rare. Large extinction-level impacts happen on timescales of tens to hundreds of millions of years. Human civilization has existed for only a few thousand. The odds are still in our favor. But science isn't about comfort, it's about understanding risk. What we can do? Even if we can't stop every interstellar object, we can reduce the danger. 1. Detect earlier. Next-generation observatories will dramatically improve detection. The Vera C. Rubin Observatory will scan the sky every few nights. It will find faster objects, fainter objects, and objects from unexpected directions. Earlier detection equals more options. 2. Improve global coordination. Planetary defense isn't just technical, it's political. Rapid information sharing, global emergency planning, clear communication. An impact doesn't respect borders. Preparation must be global. 3. Build knowledge, not fear. Understanding interstellar objects helps reduce panic. Fear thrives on mystery. Science removes mystery. The more we study these objects, the better we understand their behavior, and the better prepared we become. The bigger picture. Interstellar objects are not enemies. They are messengers. They tell us how planetary systems form, how material moves through the galaxy, how common or rare catastrophic events truly are. They force us to look beyond our comfort zone, beyond the idea that Earth is protected by familiarity. A final reality check. Earth has been struck before. It will be struck again. That is not speculation. It is geological fact. The question is not if, it is when, and from where. Interstellar objects add a new layer to that question, a layer we are only beginning to understand. But understanding matters because knowledge is the first step towards survival. And that brings us to the final thought. Earth does not exist in isolation. It moves through a galaxy filled with motion, chaos, and history. Sometimes that history passes right through our neighborhood. And when it does, our future depends not on fear, but on preparation.
Can we stop an interstellar object? The limits of planetary defense. When the idea of stopping an asteroid comes up, most people imagine something familiar: a spacecraft, a controlled mission, a calculated push. Humanity changing the course of a cosmic threat. And for solar system asteroids, that idea is no longer science fiction. But interstellar objects are different, and that difference matters more than most people realize. The one thing all planetary defense plans depend on. Every planetary defense strategy
Every mission concept depends on a single factor: time. Asteroid deflection works because asteroids orbit the sun. They come back. They can be tracked years in advance. NASA's DART mission proved this. By impacting a small asteroid moon years before any danger, scientists successfully changed its orbit. Small push, big result. But that success hides a critical truth. It only worked because we had years of warning. Interstellar objects break the timeline. Interstellar objects don't orbit, they don't return. They appear once, and they move fast. In the worst-case scenario, an interstellar object could be detected weeks before impact, days before impact, or not at all. There is no realistic way to launch a deflection mission in that time frame. Rockets take months to prepare. Spacecraft take years to design. Missions require planning, testing, and coordination. Interstellar objects don't wait. Could we use nuclear weapons? This question always comes up. Could we destroy an interstellar object with nuclear weapons? The honest answer is, not reliably. Nuclear deflection concepts depend on precise targeting, long preparation time, and known object structure. With an interstellar object, structure is unknown, composition is unknown, warning time is minimal. At extreme speeds, even fragments become deadly. Breaking an interstellar object apart might make the situation worse. Instead of one impact, Earth could face a shotgun blast of high-velocity debris. What about lasers or exotic technology? You may hear about space-based lasers, gravity tractors, or advanced propulsion. These ideas are promising for the distant future, but today they exist mostly on paper. None are operational. None can respond in days. None can handle an object arriving unexpectedly at interstellar speed. The hard reality. With current technology, a fast interstellar object detected late cannot be stopped. The only realistic responses would be emergency warnings, civil defense measures, and impact mitigation after the fact. That's not defeatism, it's physics. Why this doesn't mean Earth is doomed. Here's the part that matters most. Interstellar impacts are rare, extremely rare. Large extinction-level impacts happen on timescales of tens to hundreds of millions of years. Human civilization has existed for only a few thousand. The odds are still in our favor. But science isn't about comfort, it's about understanding risk. What we can do. Even if we can't stop every interstellar object, we can reduce the danger. 1. Detect earlier. Next-generation observatories will dramatically improve detection. The Vera C. Rubin Observatory will scan the sky every few nights. It will find faster objects, fainter objects, objects from unexpected directions. Earlier detection equals more options. 2. Improve global coordination. Planetary defense isn't just technical, it's political. Rapid information sharing, global emergency planning, clear communication. An impact doesn't respect borders. Preparation must be global. 3. Build knowledge, not fear. Understanding interstellar objects helps reduce panic. Fear thrives on mystery. Science removes mystery. The more we study these objects, the better we understand their behavior, and the better we prepare become. The bigger picture. Interstellar objects are not enemies, they are messengers. They tell us how planetary systems form, how material moves through the galaxy, how common or rare catastrophic events truly are. They force us to look beyond our comfort zone, beyond the idea that Earth is protected by familiarity. A final reality check.
Earth has been struck before. It will be struck again. That is not speculation. It is geological fact. The question is not if, it is when, and from where. Interstellar objects add a new layer to that question, a layer we are only beginning to understand. But understanding matters, because knowledge is the first step towards survival. And that brings us to the final thought. Earth does not exist in isolation. It moves through a galaxy filled with motion, chaos, and history. Sometimes that history passes right through our neighborhood, and when it does, our future depends not on fear, but on preparation.